to recap the integration techniques we've learned so far, we have a U-sub technique, which goes back to calculus AB. We have trig identities that we can use. We have long division. We have divide and conquer, which is particularly useful for when we have fractions, integration by parts, and trigonometric integrals. And when we look at this new technique, it's still going to be along the lines of trigonometry, but this is where we're going to use right triangle trig and do substitutions so that we can take expressions that have Pythagorean-like patterns in them and make them easier to integrate. So if we look at these identities here, these are, some very familiar identities that we've been working with, and you certainly have been working with for years. And we've been working with these in the last section. And what we're going to do is we're going to use these identities and recognize these patterns in. We're going to recognize these patterns in our integration and substitute those patterns out. So when we have a pattern that looks like this, and today's focus is going to be this pattern of a squared minus u squared and taking the square root of that difference, we're going to do what we call a sign substitution. And so what we have here is, if we take a look at this pattern, we know our basic Pythagorean pattern looks like we have our hypotenuse here. We have our leg. We'll call that leg 1 and leg 2. And so we have this basic Pythagorean pattern of leg 1 squared plus leg 2 squared equals hypotenuse squared. And so that's our basic Pythagorean pattern. And then as we start to want to get expressions for the legs, we would subtract this and take it to the other side. And so that's the type of pattern we see here. Is we see that pattern that has us really giving us an expression for one of the legs. And so in this case, and I'm not being too specific with things like a squared plus b squared plus c squared, because the a in these expressions doesn't necessarily mean a leg. Like in this situation, it might be in this situation it's a hypotenuse. So I'm just being really general with this description here. And so when we have patterns in our integrals that are in this sort of pattern of a number squared minus u squared, then we're going to do a sign substitution here to substitute those out and substitute in a trigonometric expression. So when we set this up over here, we can see that in terms of the angle theta, we're going to set up our trigonometric integrals. So we know we have a sine of theta is opposite over hypotenuse. So we're talking about opposite over hypotenuse. And so we're talking about u over a. And that's where this expression is coming from. And then we have our cosine theta, which is adjacent over hypotenuse, which is the adjacent side is the difference, that pattern that we'll start to see in the integral. So it's the square root of a squared minus u squared over hypotenuse, which is a. And that's where this expression comes from. And looking at this example here, we have a fairly complicated looking integral. And we can see that we have this a squared minus u squared pattern. And so in this situation, we have our a squared minus u squared pattern, and that's going to look like 5 squared minus x squared square root. So we can go ahead and set up the right triangle here. And when we set up the right triangle, we notice that wherever we define theta, we want the variable of integration to be opposite that that angle. So we have the variable of integration here. This tells us what our hypotenuse is. So our hypotenuse is 5, and then that leaves this adjacent side to be 5 squared minus x squared square root. And so we can set up then, what we do then is we look at this and we know that we need to substitute out a differential expression. We need to substitute out an expression for x squared, and we need to substitute out an expression for the radical. And so that the whole idea then is to build those 3 components so that we can substitute those out. And so we start with our definition of x, and x is taking the sign, the SohCahToa expression. So we take the sign expression from SohCahToa, and we solve it for x. So we have x is 5 times the sine theta. And then we can differentiate that. So the derivative of 5 times sine theta is 5 cosine theta, d theta. So now we have something to substitute out. Oops, we have an expression to substitute out the differential dx. Then we can come back here and we have an expression for x, so we can get an expression for x squared. So when we square that, we get 25 sine squared theta. And so we notice we're starting to see sine squared theta, so we might have to use techniques from the previous section with some trig identities as well. And then we can go ahead and set up our ratio involving the side here with the radical. And so we usually want to involve the simplest sides we possibly can. So in this situation, we want to set up a trig ratio involving the radical and the number 5, because the number 5, when placed in an integral, is easier to integrate than the variable x. And so we're going to go ahead and set up our cosine theta. So here's theta, adjacent is the radical, 5 squared minus x squared, and the hypotenuse is 5. And so we have, for the radical then, solving this for the radical, we have 5 times cosine of theta. So that is the expression that we're going to use to substitute out for the radical. And so as we write this integral then, we're going to substitute all of these expressions in. And the 10 is just a number, so we're going to leave that right there. X squared is 25 sine squared theta. Dx is 5 cosine theta d theta. So we have that expression, which doesn't look that friendly, but can be simplified, and once it's simplified, it's really not that bad. So if we look at simplifying this, oh, and you know what, I actually forgot to put in scooch that over a little bit, and also want to put in the expression for the radical, which is 5 cosine theta. So just to kind of slow down a little bit here, we had a differential dx, and for that differential dx we threw in that expression, and that shows up right here. I tried to put it kind of right in the dx location. We have an expression for x squared. So x squared is here. This is the expression we're going to substitute in, and so we find that expression right there. And then we have an expression for the radical, and here's that expression for the radical, and we're going to substitute that right there. And so again, looks kind of messy, but we can go ahead and do some simplifying here. And so we look at this and we see that we can get a 5 to cancel with a 5, a cosine theta to cancel with cosine theta, and after we do that, and we've got 10 over 25 here, which we can factor out as 2/5. So let's go ahead and factor out the 2/5, and then what we're left with here is 1 over sine squared theta, d theta. And in looking at integrating this, if you remember back to your integrating your trig identities, if we would write this in terms of cosecant, because that's just the reciprocal of sine, we have that expression. And then cosecant is one of those things that you find in the front of the book. I call that an FOB. And so the front of the book, the integral of cosecant squared theta is opposite cotangent theta. So we end up having 2/5 cotangent theta with an opposite there. And so that equals plus c. So that equals minus 2/5 cotangent theta plus c. And then we also have to do the substitution back into terms of x. So if we come back up here and talk about cotangent, cotangent is the opposite of, the reciprocal of tangent. So we know that cotangent, if tangent is opposite over adjacent, this is adjacent over opposite. And so that being the case, then cotangent of theta is going to be adjacent, which is the radical, and opposite, which is x. So it's going to be 5 squared minus x squared over x. And so that's what we have to substitute back in then to this answer, so that we have our answer in terms of the variable we first integrated with respect to. So that is going to be the square root of, I'm just going to write it as 25 now, minus x squared divided by x plus c. This integral also has that familiar pattern. So if we look at this, we know that we need to get an expression for x. That's got to be present in any of these problems that you do. We also need to be able to substitute out a dx, and we also need to be able to substitute out the pattern 25 minus x squared square root. So those are the substitutions we need to make. So if we set up a right triangle here, and we go ahead and set it up with theta and the variable across from theta, and looking at this pattern here, this is another 5 squared minus x squared pattern, so we know the hypotenuse is 5, and then we know the adjacent side is the expression for the radical, 5 squared minus x squared. Then we can go ahead and set up our x here, so we'll set up our sine expression. Sine theta equals opposite over hypotenuse. So solving that for x, we get 5 sine theta. And then we can go ahead and set up our cosine function. Cosine equals adjacent 25 minus x squared over hypotenuse 5. So we end up with 5 times the cosine of theta. And then we can go ahead and take the derivative here to get the expression for the differential expression dx. And so the derivative of sine theta is 5 cosine theta d theta. And then we can go ahead and coordinate our substitutions here. So I've got a dx I'm substituting out. So I'm going to use this expression here. And then I've got a radical that I need to substitute out. So that is that expression there. You notice there is no x in this expression. So there will be no substituting this expression into the integral. It just doesn't exist. All this was done, all this was used for was to set up the expression for the differential. And so if we look at this, then we have the integral of 1 over 5 cosine theta. That's the radical, substitution for the radical. And now the substitution for the differential is right here. And so that is times 5 cosine theta d theta. And if you notice, we have a lot of canceling. The 5's cancels, the cosine thetas cancel. So what we're left with is just 1. So when we integrate, it's kind of an interesting scenario here, we're left with 1 d theta. And when you integrate 1, you end up with whatever the differential variable is, and the differential variable is theta. So we end up with an answer of theta plus a constant. So theta is a degree measure or an angle measure, a radian measure. And so we need an expression for theta, which means we need to come back up to the differential or the trigonometric expressions we have up here, and we have to decide which one to solve for theta. So my advice is solve for the easiest one. So if we have these two different expressions, SohCahToa expressions. So I'm just going to rewrite those expressions down here. So if we have sine of theta equals x over 5, that's a lot more simple than cosine of theta equals the square root of 25 minus x squared over 5. And so the idea is to solve this for theta, we can just take the inverse sine of both sides, and we have the inverse sine of x over 5. That is what we should be plugging into up there. We could solve this for theta if we wanted to. We could go ahead and say this is the inverse cosine of that expression. 25 minus x squared over 5. Okay, so we could do all of that solving in here, but it's much more complex. It's not wrong. It's just an alternative answer. And so if if we go ahead and get the answer here, then I'm going to choose using the inverse sine of x over 5 plus c as my answer. That's one option for an answer. The other option would be inverse cosine of 25 minus x squared over 5 plus c. And so we could really make an expression. We could really make an expression for each of the 6 trigonometric functions that that's mathematically equivalent. I can almost promise you this is the one that would be the answer in the back of the book. If you were ever to work out of a traditional textbook, and be checking your answers in the back of the book. But all of these are mathematically equivalent, and we can prove that if we would graph them all. So with all of these methods that we have now for integration techniques, we can now add trigonometric substitution to the list of methods. And we've gone through one of 3 substitutions we can do, and that substitution was the a squared minus u squared. There's 2 other ways to rearrange Pythagorean's theorem and get a radical expression, and those will be parts of the next 2 videos.